Our next speaker is Wang Shida. He is a fourth-year PhD student in National University of Singapore in the Department of Mathematics. He works on theory for machine learning, in particular sequence modeling. He is going to share with us some of his recent work on state space models. Wang Shida.
Hello, everyone. Today I'm going to talk about state space models. Before talking about state space models, I'll first briefly talk about recurrent neural networks and the difference between recurrent neural networks and state space models. After talking about these two models, I'll emphasize the two results of my presentation. One is the universality, and another is the curse of memory. By universality, I mean the model, you can use the model to learn whatever relationship you want to learn. And by the curse of memory, since we are working with recurrent models, such kinds of models store the information in the hidden state. But when the sequence gets longer, the information stored in his hidden state will get decay. So first, recurrent neural networks. Recurrent models are a family of models used to learn sequence-to-sequence relationships. Assume we want to model the relationship between input sequences xk and output sequences yk. Here, I just give the simplest nonlinear recurrent neural networks. As you can see, this hidden state is evaluated using the iterative equation. And the sigma here is the nonlinear activation function. For example, tench is usually used to update the hidden state. And after the evaluation of the hidden state, the output yk is evaluated just by some linear transform. So this is the simplest recurrent neural network. And some popular models based on this are long short-term memory, the LSTM model, and gated recurrent unit, the GRU model. But such kinds of models are kind of slow in the sense that each time, if you want to evaluate hidden state at time t, you need to start from hidden state h0 and do it iteratively. Now we come to, here is just some notation, like the M is the hidden state and W, U, B, C are the trainable parameters. And in practice, these trainable parameters, W, U, B, C are trained by optimizer like Adam. Now it comes to the state space models. State space models add the activation function in a layer-wise approach. As you can see here, compared with the recurrent models, which has the recurrent activation to update the hidden state, in state space models, the hidden state is just updated using a linear dynamical system. And later, I'll talk about why it can be faster than recurrent models. And the only nonlinear activation is added in this layer-wise approach. And this layer-wise approach allows us to speed up the evaluation because each time given the input, and then we use linear dynamical system to evaluate the hidden state, and then we evaluate the output. So basically, all these steps can be parallelized. And the main advantage of state space models over recurrent neural networks are the speed. Because for linear dynamical system, it has this linear form, and we can do some eigenvalue decomposition, and then this hidden states are actually decoupled into different dimensions. And then while the recurrent models is limited to iterative evaluation for hidden state, the state space models can be accelerated using techniques such as associative scan or fast Fourier transform. And the speed difference is mainly t versus log t, because in state space models, when we use fast Fourier transform, we just need log t time to evaluate the final hidden state. So here are the introduction part for recurrent models and the state space models. Now we come to the first result for these recurrent models. The universality part. For for any sequence-to-sequence relationship and any tolerance epsilon, it has been proved in some paper, it dates back to 1993, that there always exists a hidden dimension M and corresponding trainable weights W, B, C, such that this model can approximate the target relationship H. Here I did not put the specific condition, but usually this sequence-to-sequence relationship needs to be nice enough. For example, it needs to be bounded, continuous, and also causal and time homogeneous. Such kinds of assumptions are reasonable because, for example, the causality, you cannot use this model to predict something in the future without the corresponding information. And the result for single-layer nonlinear recurrent networks are known in 1990s, but recently we just gave a constructive proof to show that for multi-layer state space models, they are also universal approximators. Why do we need this? The reason is that for simple linear dynamical system like this one, actually it can only model the target functions such as the linear functionals. But in practice, most of the sequence-to-sequence relationships, such as machine translation or language modeling, they are not linear functionals. Therefore, we need some nonlinearity to increase the expressive power of our models. And our work shows that actually multi-layer state space models are good enough to approximate any nonlinear sequence-to-sequence relationships. So this is the positive part, that state space models are good enough. We can use it to learn whatever we want to learn. However, these models also have some problems. And since it is a recurrent model, a natural question would be whether it also inherits some problems of traditional nonlinear recurrent models. And the answer is yes. I'll just illustrate with this linear system because most of the part can be seen from linear system. For simplest linear system, if we consider this update, hk plus 1 equals to whk, and if we assume this iterative process is bounded, then we know the eigenvalues of this recurrent weight matrix W needs to be in the unitary disk. And furthermore, if we assume it is to be decaying, or if we consider the stability constraint, then the eigenvalues needs to be the norm of the eigenvalues needs to be less than 1, and then it means this hidden state, when we iterative it, it will be decaying, and the decay speed is actually exponential for some positive constant beta. And this is just for linear system, and it is autonomous. There is no input coming. And for linear system with input and output, actually we can define a memory function. This memory function characterizes what is the system memorizing about the previous input, like x0. And we use this function to characterize the memory function so that we can prove a similar result. That is, the memory of x0 in output yk is actually decaying exponentially. This is just a natural result for the above hidden state decaying. Then this is the result for linear system, and in our recent work, we managed to prove that actually for nonlinear models and state space models, no matter the recurrent activation or layer-wise activation, as long as you generalize the concept of memory function properly, then they are also decaying exponentially. In other words, the recurrent activation and the layer-wise activation, they does not change the exponential memory decay pattern. So it's always decaying exponentially. So this is the common feature of such kinds of recurrent models. Okay, thank you for listening. And this is my state space model paper link. Feel free to check out if you want to know the details. Thank you.